Good morning, dear students. Welcome to this session on pre-stressed concrete. Uh, Till the last session, we have talked about the uh, uh, all types of losses that are possible in the pre-stressed concrete, both in pre-tensioning and post-tensioning members. Now, let us deal in terms of total losses. Say if you are designing a pre-tensioned concrete member, so you have to uh, calculate the total loss of pre-stress, then use the effective pre-stress available in the concrete. Okay, that can be transferred to the concrete. So that is what is required. So in such cases, you have to calculate total losses. Okay. Now we have seen till the last session each individual loss of pre-stress. What are the formulae? How you calculate it? Now you have to calculate in terms of total loss for a particular case, like pre-tension member, what will be the total loss? Post-tension member, what is the total loss? Okay, so let us see that in that aspect. Right. Generally, as I just mentioned, design of pre-stressed concrete members, you have to assume total loss of stress as percentage of initial stress and provide this for design computations. Okay. Since the loss of pre-stress depends on several factors that we have seen, like shrinkage, creep, relaxation, elastic shortening, likewise curing, when degrees of pre-stress and method of pre-stress, like that. It is too difficult to generalize the exact amount of total losses of pre-stress. You can't generalize, just like at 20% will be lost, 30% will be lost. Okay, but however, typical values of total loss of pre-stress that could be encountered under normal conditions of work recommended by Lin are given in the tabular form to follow, that we will see. And to avoid or to reduce relaxation loss, friction, anchorage slip, temporary overstressing is done. Okay, I mean, instead of providing thousand, say for example, you want to jock the tendon for 1000 megapascal. Uh, just go for little bit higher value of stress, over stressing. Then that will reduce the relaxation loss and frictional anchorage slip losses. Okay, and this is taken from Annexure D of IS code, where it is mentioned that the effective pre-stress F suffix PE, effective pre-stress after all losses is not less than 0.45 FPU, where FPU is the characteristic tensile strength of the tendon, which means what? 0.55 means 55% of the pre-stress loss is also can be encouraged. Okay, even though if 55% is lost, but it cannot be the highest percentage of loss. Uh, the the total loss of pre-stress cannot be more than 55%. Okay, so effective pre-stress after all losses shall not be less than 45% of characteristic strength. Okay, this is design requirement. Right. Just now I said no. Lin has given some values of loss of prestress. That is this table. It's for general use. Okay. Anyhow, for design purpose, we'll be following the IS code 1343-2012. Just for the sake of no, just uh, to have a number, general number. These are the losses that can be taken. Elastic shortening, 4%, 1%. Creep of concrete, 6%, 5%. Shrinkage, 7 and 6. The creep in steel, nothing but relaxation of steel. Okay, creep in steel is nothing but relaxation. So 8% and 8%. So total put together, pre-tensioning you can have, or you can just take the 25%. For post-tensioning you can take 20% of the losses. Okay. So eta is a term which is introduced like a reduction factor for loss of pre-stress. Reduction factor, which is effective pre-stress divided by stress in tendon after or at transfer. That is this one. If you follow the IS code notations, if it is FPE divided by FPU, okay, that is the notation to be followed. The textbook follows PI as stress at transfer, whereas IS code follows FPU as the characteristic strength. The, I mean steel. Okay, right. So let us calculate whatever calculations have done independently, each category wise. Now we do all at once. Okay. So just taking an example, a pre-tensioned beam, 200 wide, 300 deep, is pre-stressed by 10 wires of 7 mm dia. Initially stressed to 1200 Newton per mm square, the centroids located 100 mm from soffit. Find the maximum stress in concrete immediately after transfer, allowing only for elastic shortening of concrete. And if the concrete undergoes further shortening due to creep, shrinkage, and relaxation of 5%, estimate the final percentage of loss of stress in wires using IS code. Now this is updated. It is like 2012. Take the latest version of the textbook. Following data is given to you. Length modulus of concrete 5700 root FCK, where FCK is 42 Newton per mm square. Creep coefficient is given, and residual shrinkage strain is given, because it is mentioned you have to find shrinkage loss also. So we need a shrinkage strain value. Okay. Right. So let us estimate first elastic shortening. If you want elastic shortening, you need modular ratio. I think you remember the formula. Modular ratio into the stress value in the concrete at the level of steel. So stress in concrete at level of steel, if you want, you need P divided by A. What is P? Stress into area of one tendon multiplied by number of tendons. So there are 10 wires of 7 mm dia. So pi d square by 4, pi 7 square by 4, okay, is the cross sectional area into 10 will give you the total cross sectional area. Okay. Right. So that is about stress into cross sectional area. 462 kilonewtons. Okay, right. P divided by cross sectional area of concrete, member size is 200 by 300. So you take the cross section area of the concrete. So this is A, this is P value, pre-stressing force. Now P into E into eccentricity, and Y value, level of steel, by I. Okay, I is again BHQ by 12, which I need not tell you. And eccentricity is centroid is located 100 from soffit. So total 300. Okay. So middle 150, total 150. So from bottom 100 means from the centroid of concrete it is 50 That's why eccentricity is 50 used, and level of steel is 50. Same, both are same. That is giving you 10.3 Newton per mm square. Now the loss of pre-stress due to elastic shortening is like uh, alpha, that is Young's modulus of steel divided by Young's modulus of concrete, modular ratio. Even you can even write m or 1 by m. Some notations are there. So alpha is used by the textbook. So alpha into stress value, that is this one, right? Right. Now the stress, I mean force after this loss or after transfer is, this is the loss value. So 1200 minus 58.8 into 38.5 is this much is the force remaining. Okay. After this elastic shortening loss. Right. Now to find the remaining losses, you have to use this value of pre-stressing force. That is what is mentioned in the given question. If the concrete undergoes further shortening due to other aspects like creep, shrinkage, relaxation. So, okay. Right. So proceed for that. Uh, P by A and P E Y by I, and 978 is the stress. Now with the by uh, removing the uh, loss of pre-stress, okay, due to elastic shortening. Right. Now, elastic deformation loss is already counted, that is 58.8 is the stress loss. And creep of concrete is by 5, that is 1.6. Creep coefficient 5 into 9.78. Okay. It is 9.78, 5 into stress into, it is like 978. It's 978. Okay, 5 into stress into modular ratio. Okay, so this is what is creep coefficient method. So that is what is this value, 89.2 Newton per mm square. Okay, so stress value is this 9.78. It's a typographical error. So 9.78 is the stress value. Right, shrinkage, just multiplying with the shrinkage strain with Young's modulus. Right. So you have to now have all these formulas with you. Phi, stress, Fc, and alpha. Okay, this is the formula for this, and this is also like epsilon into capital ES, epsilon shrinkage strain, whatever is mentioned here, shrinkage strain epsilon S, capital E suffix S, that is the formula for this. And relaxation, I told you, it is like just a percentage in the given stress value. It is set 5%. Relaxation loss is 5%. So 1200 is the stress value. Out of 1200, 5% is the shrinkage, relaxation loss. So all these put together, total loss is 271. So total 1200 we have induced, out of which 271 is lost. So what you have is 928. Okay, what the remaining stress, the percentage, loss value divided by initial into 100. So total 22.58% is the loss of pre-stress. So this is how we calculate all the types of stresses put together. Okay. And now you can see, because it is pre-tension member, you have got only four types of losses. There won't be any friction loss. There won't be any no anchorage slip loss. Okay, because it is pre-tension member, we don't provide any anchorage, and there is no relative movement of the tendons with respect to concrete, because once the tendon is tensioned and we pour the concrete gets hardened and we cut the wires, and the concrete holds the steel tightly. There is a bond there. So that is how it is. Whereas post tensioning is different. Concrete is made ready. We keep a duct. We leave the duct for placing the steel inside, and then we will tension it. So tendon is going to move. Okay. So that is how it is. Right. Right. Going for the uh, next example. Same pre-stressed concrete pile, 250 square, contains 60 number of pre-tensioned wires, each of 2 dia, uniformly distributed over the section. The wires are initially tensioned on pre-stressing bed with a total force of 300 kilonewton. Calculate the final stress in concrete and percentage loss of stress in steel after losses. Following is the data. Uh, Creep strain is given, shortening due to creep, total shrinkage strain is given, relaxation percentage given, pre-stressing force given, which is already there, 300 kilonewton. So let us calculate the initial stress in concrete just by force divided by area. It is square number, square 250 by 250 square, so 4.8 Newton per mm square. Modular ratio ES by EC. ES is 210 by 32. Okay. The initial stress in steel wires is like force by cross sectional area. Okay. So that is what is 4 point. 1590 is the stress induced in steel wires. Force is 300. Cross sectional area of the cross sectional area is like 2 dia wire. Okay, so 2 dia wires, there are 60 in number, so total area will come to 188.4 is equal to 1590 is the stress in steel. Okay, now let us calculate elastic deformation loss. It is simply by multiplying alpha into fc. So what is fc? 4.8 is the stress in concrete, alpha is 6.58. So this is the loss value. Creep coefficient given, multiplied by stress multiplied by Young's modulus. Okay, So phi, okay, uh, creep strain is given instead of creep coefficient. Now the other method, okay, creep strain epsilon c, okay, whatever notation you use it for, so that you can follow. So creep strain multiplied by the stress value in concrete multiplied by Young's modulus of steel. Okay, so that is coming to 30. And shrinkage of concrete, the shrinkage strain is given to you 200 into 10 power minus 6. Shrinkage strain into Young's modulus. Okay, and then your relaxation loss, just now in the last problem also we have seen it's a percentage. So 5% of 1590 is lost. That is this way. So total put together 183. So effective stress is 1590 initial stress, loss 183 and remaining 1407. Final stress in concrete is, this is the stress into area, and 188.4 is not 188 1884, it is 188.4 divided by cross section area of concrete. Stress into area, pre-stressing force, remaining force, so that is coming to 4.26. Okay, final stress in concrete. And percentage loss is 183 divided by 1590 into 100. 11.6% is the loss of pre-stress in concrete. Okay, right? So that is about the second example of pre-tensioning case. So these are the two such examples for pre-tension members where you have to find four types of loss of pre-stress and accordingly you have to use them. Okay, we'll see the other examples in the next session. Okay.